Hey everybody. Today we're talking about significance testing for a single variance. It's all based on the idea that sample variance, when scaled appropriately, has a chi-square distribution. So when we test a null hypothesis about variance, we're going to take the sample variance we get, scale it, and then see where that test statistic falls in the appropriate chi-square distribution. Pretty simple. Let's see how it works in practice. This is a pretty typical example. A cereal manufacturer has a procedure where they know they have a certain variability in the fill of their cereal boxes. They want to reduce it. Under the old system, they knew the variance was 0.64 grams. Under the new system, they just have a sample size 50, and they have found a sample variance of 0.36 grams, so less. Is that difference statistically significant? We'll test at significance level alpha equals 0.05. So here we have a one-sided alternative hypothesis that the variance is in fact less than it was, 0.64 grams. So let's compute a chi-squared statistic for the sample that we got. We take the sample variance, 0.36, we multiply it by the number of degrees of freedom, one less than the sample size, divide by the variance under the null hypothesis, and we get a test statistic of 27.56. It's a one-sided alternative hypothesis, so we want the probability of randomly getting a chi-squared value less than or equal to that in chi-squared of 49. We compute that probability using technology, and we get 0.006. Obviously, that's less than the critical value. We selected alpha equals 0.05, so we reject the null hypothesis and conclude that the new procedure does in fact reduce the variability of fill in those cereal boxes. Let's look at one with a two-sided alternative, because this has one subtlety that we need to pay attention to. So here's a sample of size 8. We're interested in testing the null hypothesis that the variance in the population from which the sample came is 25. The alternative hypothesis is just that it is not 25. We'll stick with significance level alpha equals 0.05. So we compute the test statistic just as before. We get 17.66. We're interested in the probability of randomly getting a chi-squared statistic more extreme than this in chi-squared of 7. So not just to the right, but also to the left. Let's see a picture. There we go. So remember that the expected value in a chi-squared distribution is the number of degrees of freedom. So in chi-squared of 7, the expected value is 7. We got 17.66. The probability of getting a chi-squared value more extreme than that on the right is just that shaded area on the right. Probability that chi-squared is greater than or equal to 17.66. Now, we'll want to double that. We want to know the probability of getting something more extreme than that just by random chance. In other words, we also want to take into account the shaded area there on the left. Should have an equal area. Now, we don't need to specifically worry about what that cutoff value is, that chi-squared value. It looks like it's a little bit bigger than 1. The main reason for the picture here is just so that we can recognize which way the inequality goes. Since we can see that our test statistic is larger than the expected value, we know that we need to compute the probability of getting a chi-squared statistic larger than that, and then double that value, as opposed to mistakenly taking the probability of randomly getting a chi-squared value less than 17.66 and doubling that value. Overall, in this case, we get a p-value of 0.027. We can conclude that there is sufficient evidence to reject the null hypothesis and accept the alternative hypothesis that in fact the population variance is not 25.